So anyway, let's get started with the quiz. I did take the time to put a key together that has everything all worked out for you. Because on the AP exam, they really don't, well, the promise has been on the AP Physics 1 exam now that there will be very little, if any, computational multiple choice. So it's all going to be conceptual, situational. So I've tried to do the same thing to you on the quizzes and on the test to just, be practicing that the whole time. So the first one is no different. We take a look at that. Which one of the following statements regarding rotation is false? Angular acceleration is constant at any point on a rotating object. Anytime you see angular, we know that we're taking like a reference line and we are rotating it around, right? So anytime you're at any point on the line, it's the same effect everywhere, right? So it could be angular acceleration we're talking about. It could be angular velocity we're talking about. At that point, for those variables, R isn't going to be a factor, is it? Now, is that true about the translational or the tangential? Does R matter there? It does, right? So when you're looking at these responses, that's really what I was picking on here. And if you look at B, angular velocity, what did I just do? I contradicted the statement that we made. For angular stuff, the radius that you're at doesn't matter. It does matter for the translational or the tangential, but it doesn't matter for the angular, so B is wrong. So the answer to the first one is B. The second one reinforces this because now I'm asking you a translational question. So if I double the distance that I am from the axis of rotation, what happens to my tangential velocity? If R doubles, and tangential velocity is the circumference that you're traveling around divided by the time that it takes for you to do that. If I double R, I double the circumference. If I double the circumference and keep the time the same, I am doubling my velocity. The answer there is B. Numbers 3 and 4 ensure that you were really paying attention to what I was asking you in numbers 1 and 2, right? So you look at 3 and 4, and it says the merry-go-round goes around at 6 revolutions per second. So I give you the angular velocity. From that, can you figure out the period? Yeah, you can, right? If I know how frequently the wheel is turning, I can figure out what the period is. If it goes around 6 times per second, how long does it take to go around once? Well, if it's going around 6 times in 1 second, each time it goes around takes how long? 1/6 of a second. Well, which one of those times represents 1/6 of a second? Answer there is C. Now, number 4 is checking whether or not you understand that if I give you the angular velocity, that it doesn't matter where you are on the circle, right? Where you are on the platform, it's going to be the same time for you no matter what. Well, if you think that it's going to be the same time no matter what, then what should the time be? The same that it was at number 3. So the answer there again is C. It doesn't matter where you move. The amount of time that it takes to go around the circle is the same as long as the angular velocity is the same. All right. Number 5 is kind of a cool question. I'll summarize it for you so that we don't have to read it off. But it basically says, the speedometer on your truck is set up so that the angular speed or the rate at which your axle is turning is tied into your speedometer. The owner unknowingly puts bigger diameter tires on his truck. Now, what does putting a bigger diameter tire on your truck do to how far you go per turn? Increase or decrease? I'm going to increase it, right? I'm going to go further. I'm going to go further with every single time the axle rotates because my outside diameter is bigger. So I'm going to go further along the ground in the same amount of time. What's going to happen to the speedometer? Is it going to stay accurate? No. it's going to think that you're going less distance than you really are because you've made your tires bigger. So you are going to read a lower speedometer reading. Does everyone see that? Now, what happens if I shrunk the radius of my tires? I would get the reverse effect, right? My car would think, my speedometer would think that I'm going further than I really am in the same amount of time. So with a smaller circumference, I'm going to have a smaller velocity than what would be read on there. So my true speed would be greater in that case. So that's how that one works. Answer there is less than. Number 6, which one of the following statements is true? Answer there is D, no tangential but a non-zero centripetal. That's for the wheels rotating with a constant angular velocity. Again, picking on a couple of things. Constant angular velocity means that your omega, which is angular velocity, is not changing, right? So if it's not changing, are you going to have an angular acceleration? No, you're not. So a bunch of those get eliminated from that, right? No angular acceleration. And if you don't have an angular acceleration, it eliminates some stuff. But does that eliminate your centripetal acceleration? What is centripetal acceleration? Who remembers? It's the only equation on the AP sheet that comes out of Chapter 5. So we did an entire chapter on centripetal force and centripetal acceleration, and we got one equation out of it. What was it? V squared over R. Good. That's the only equation there. And if you think about that, does a point on the outside of the tire have a V? It does have a tangential velocity, right? And does it have an R? Yeah. So you know you have a centripetal acceleration. The tangential one, no. Okay? Now let's go to the problems. I think everybody the moment. All right. Here's why you struggled. You were looking at this problem, and it's a mix of the variables that we've had in 2 different units. Chapter 2, which is the kinematics in 1 dimension unit, right? Linear motion, motion in a straight line. And then Chapter 8, where we customized what we learned about things that are going in a straight line to talk about things that are spinning. And one thing that you have to come to realize is that there is a common link. There are several common links, actually, to go from one to the other. First, and we went over this in the second discussion that we had. Remember, I did 8-1 through 8-3 where we just went over the equations in one conversation, and then we did how are they related to each other in another. And we came up with this. The velocity that we learned about in linear motion is related to the velocity of things that are turning in this way, and A is related to alpha the same way. And I derived those for you in class, and that's where I think I lost some people. I started showing you where the d theta over t came in, and then we clumped that together, and that's how we got r omega. We talked about arc length making that happen, and some people just got lost in the math. If you got lost in the math, here, refocus. You know these. If you want me to jog your memory, there was a part in that conversation where I said, hey, these are not on your AP sheet. These are something that you might want to either commit to memory, put them in your calculator, do something so that you had them at your disposal, right? Those were the 2. Now, I'll show you why they become important. I'm given the velocity, and I'm given the diameter from which I can get, if you know diameter, you know radius, right? So from the diameter, I can get the radius. From the radius and V, I can get omega. I need that. And I know this. I can get this. Actually, initial omega, right? Because ultimately, what's it going to end up doing? What's she trying to do with her bicycle? She's trying to stop, right? So she's trying to stop, and she's starting at 24 meters per second. Now, so these two, remember I was talking about, just a couple minutes ago, I was talking about connections between linear motion and rotational motion. These connections, there's another connector. What is it? It's the one variable in all of these equations that doesn't care about direction, whether you're spinning or going straight or anything else. What is it? Good. Louder? Did you get that in the mic? Yeah, you said time. Excellent. Time, right? Why does time work in both cases? What is it? What kind of quantity? It's a scalar quantity, right? And so if I could figure out time with one set of equations, whether it be the linear motion ones or another, it will work. So I could take the time and figure it out with one set of equations and then use it in the other ones. That's handy. That's the part you guys missed, most of you. Because here's what we've got. I've got x, I've got v initial, and I've got v final. From v final, v initial, and x, I can get a. Then once I have a, can I get t? Yes. So I had to do a bunch of linear motion stuff to get the time. And then once I got the time, I could use the circular stuff that we know to get the answers that I was looking for. That's a lot of steps. You guys aren't used to that many steps sometimes in your problem solving. But none of the steps are difficult. Here's what I mean. If I gave you the problem, girl's riding her bike. She's going 24 meters per second. 120 meters from the intersection, she applies her brakes to slow down and stop. And I ask you, how long does it take for that to happen? Everyone in this room can do it. We did it in September. Now, I don't know if you can do it still, but you knew how to do it before. So let's review that. V final squared equals V initial squared plus 2 times A times X. Question?
Yeah, can you show us the factor label from inches to the meters?
Yes.
I feel that seems off.
It's not, though. The factor label to go from inches to meters is 0.0254. There are 54 centimeters to do the I know. I found that out first period. He gave you the wrong one. So if you're great and you use 2.2, which is not right, that's okay. You're going to get credit. I'm not going to, first of all, and most importantly, this question came up first period. You don't have to memorize any of those things. If on the AP exam, if it's not on the front sheet, which is an all factor label sheet anyway, right? It's got all these physical quantities on there and all that. If it's not on there, they give it to you directly in the problem. You don't need to memorize any conversion factors. And that's true for me too. So I wasn't here yesterday, I apologize, and you got the wrong factor label, that's okay. You get credit, so just ignore. Your numbers are going to be a little off from mine, and just know that they're going to be. It's not 2.2. 2.2 is actually how many pounds are in a kilogram when you're on Earth. I don't know how that number came out, but that's not right. 2.54 centimeters per inch is right. So that's kind of a problem that we uncovered first period. But don't worry about it. So this is the true R. If your R is off from there a little bit because you used the wrong factor, the wrong conversion factor, that's okay. Just follow along. Pay attention. We don't use that for a second anyway. Right now, I feel like we need to find the time. Actually, no, wait. Let's go back a step. A asked us for the angular velocity. The angular velocity is that guy, right? And I know this, and I know this. So what do I have to do to get the angular velocity? 24 divided by whatever you got for r. Some of you got a different r than me. So whatever that r is, if you took the velocity and you divided it by the radius, whatever radius you converted to, give yourself credit. That's a +1. And that's the answer for part A. I was already jumping to part B without confirming that for you. Part B, we need to get to time so that we could use the time in the equations for rotation. So here's how we're going to do it. V final squared equals V initial squared plus 2 times A times x. Substituting in our numbers. V final is 0. V initial was 24. The distance covered 120. What's the only thing I don't know? A. When you do the math, you end up with an acceleration of negative 2.4. If you did that, and again, maybe there should have been no conversions here, but if you did that, you have that equation on your paper, that's a +1 right there. I did not ask you for A, but if you figured it out, knowing that you needed it moving forward, we're going to give you a point for that. Finding T is really easy. Again, 0 equals 24 plus negative 2.4 T, and then you find out that time is equal to 10 seconds. Exactly, 10 seconds. Yes?
What if we switched final velocity and initial velocity, so instead of putting 0?
So you ended up with a positive. You would have ended up with a negative time, which probably may have freaked you out as well, but
No,
or you just ignored the negative at the
it was just a negative, it was just a negative acceleration.
So then when you plugged A in, you didn't put a minus in, and then you had those others flopped. Yeah, so it's like you canceled them out, but you did it inadvertently. Just take off actually, just circle it so that you remember and don't take off any points for that. No better next time, for sure, right? Because you're slowing down. That means your V final better be smaller than your V initial. So no better for next time. All right, now, once I have the time, finding alpha is super easy. Because this is why I needed to do all of that stuff with the linear motion stuff that we did at the beginning of the year. Once I know the time, these two I knew already. Right? This I know is going to be 0. This I know because I figured it out in part A. Whatever you had in part A goes here. 0 goes here because the tires on the bike stop. So you take those two, and the only missing link was the time, which now we know is 10 seconds. So you go 0 equals 70 radians per second plus what we're looking for times 10. So if you do this right, you end up with minus 7 radians per second squared. Now, why is it minus? Same reason it would be minus if we were doing linear motion, right? Acceleration, when you're speeding up, is positive. Deceleration, negative, right? If the wheel is turning faster and faster and faster, so in other words, if the angular acceleration is making the angular velocity increase, then the alpha is positive. If the wheel is slowing down, then alpha is going to be negative. It's slowing down, so we expected minus, yes.
Why couldn't we just, so after we find A, why can't you just use this equation up here? A equals radius times alpha.
You can.
Then why do you do that? So much more work.
Because, where did you want to do that?
After you find A, because you get the same answer.
Yeah, you could do that. Well, the question was, why didn't you just use A equals R alpha? The answer is, it doesn't matter. I can use it. It doesn't matter which way you do it. Some is connection. What I'm telling you is, I mean, this is the easiest way to go whenever you can, right? And I did all the work to get to A, so I could have just plugged here with R. Or, I mean, to me, it's not that much harder, right? If I know this, you're going to get to the same place. So Jordan just worked through in his mind another solution to the problem. There were even other solutions to get to the time if you wanted to. I can't show you every possible way to solve the problems. I'm going to show you multiple ways when I can, and he just gave us a second option. But is it okay if you see on the paper A equals R alpha, and you know what A is and you know what R is, so you just do A divided by R equals alpha? Absolutely not. Will you get a different answer from me? No, you don't. It's the same answer. Okay? The last one, centripetal acceleration. V squared over R. That was a plug and chug. If you missed that one, we're in trouble. I gave you V, and I gave you R. So the V was 24 meters per second. The R was 0.343. You just plug those in, V squared over R, and you end up with 1679.3. And that should, my bad, that should be meters per second squared. Okay? Moving on. Yes? Yeah, let's go back over that real quick. So we're going to go 2 points for A. Actually, 1 point for A, 2 points for B, and 2 points for C. Yes, I'm trying to give up as many as I can. The centripetal acceleration one was the easiest, so we're going to make that worth the max. All right. Now, the second problem, kind of like this problem. It's kind of cool. We won't get through all of it because I only have 4 minutes. So real quick, basically we have a lacrosse player that's starting with the stick parallel and releases the ball when it becomes vertical. Here's what a lot of people in first period at least missed, and some stats. From that parallel position to the vertical position, with the 1 meter stick, they were able to get the ball to 10 as it left the stick. Now, a couple of things. First of all, the one thing that my students in first period didn't notice that they were like, oh, can't believe it, is that I gave you theta. Did you notice that? I see a lot of people going, no. I gave you theta, didn't I? You started here, and you went to here. What is that? What is that? From here to here. How many degrees? 90 degrees. All right, now let's put it in terms of things that we can actually use. How many radians? Well, how many radians is this?
2 radians.
1 time around is 2 pi. Okay. Well, how many times around did I go? 1/4 times around, right? Well, what's 1/4 of 2 pi? Pi over 2. Excellent, thank you. It's pi over 2, right? 90 degrees is pi over 2. 180 degrees is pi. 270 is 3 pi over 2. And then if you go all the way around, it's 2 pi. That's where so we start with the whole circle being 2 pi, and then we know we only went 1/4 of a circle. So I gave you theta. I also gave you R and V. So what else did I give you? I gave you omega. And I really gave you an easy omega because I made R what? 1. So 10 meters per second was the velocity of the ball coming out of the racket, or the stick, I'm sorry, and 10 radians per second was the angular velocity of the stick as well. Does everyone see that? Now, what was the initial angular velocity? When it's here, 0, and it gets up to 10, and I know the theta. So now I know theta, I know omega final, I know omega initial, and the rest of this problem is history. This is pretty easy, right? Does everyone see? The crucial part that I felt as I was watching the faces in the room, both periods, is the pi over 2 thing. Yeah, the theta was missing in your mind. But if you look at the picture, you see it starts here and it goes to there. So I'm giving you that. And then once you have that, then it's plug in. So if theta is pi over 2, so if I use omega final squared equals omega initial squared plus 2 times alpha, I can get alpha. It's the only thing I don't know is the acceleration. And then we end up with the acceleration being 31.8 radians per second squared. Now to find t, we just plug in 10 equals 0 plus 31.8 t, and t is seconds.